Okay, thank you for watching my March meeting talk. My name is Christian Boyd from the University of Illinois at Urbana-Champaign. I'm going to be speaking about the linear magnetoresistance and LSCO, really discussion about classical disorder versus possible critical scaling. And this was done in collaboration with my advisor, Philip Phillips. The first thing I want to talk about is really a discussion of what makes strange metals strange. So my original section was meant to be the normal state of high temperature superconductors. I assume by now many people would have shown phase diagrams. I'm going to jump into it and show some data from a 2018 sample of LSCO near optimal doping. This is a prototypical T-linear scaling that we know about in cuprate strange metals. And also there's a similar kind of duality that we see in the iron nictide superconductors near optimal doping. Both have T-linear resistivities, which is strange metallic. Interestingly, recently we've seen data that at low temperatures we also see an apparent regime of bilinear, or a linear scaling in the magnetic field for the resistivity. This is for LSCO, and we also have this case for the iron nictide sample. So I think we need to have a discussion of why a linear magnetoresistance is interesting. Is this unique to strange metals? And what are some other avenues? And I want to talk about just a typical metal. Aluminum's kind of a run-of-the-mill example here, and let's go through some historical data. This was analyzed by Kohler, but not taken by him. And we can see that the relative change in the resistance, so as we turn on a magnetic field versus its zero field value, as a function of the magnetic field, so down here, is initially quadratic. So at low fields, this should increase, it's quadratic, and then at stronger fields, so here's the initial quadratic rise, but once we go up to stronger fields, there's a saturation behavior. Okay, and this is a very typical case. It's not so hard to derive, and it kind of just follows from some dimensional analysis and Drude theory, so let's go through that very quickly. I want to talk about a relaxation time approximation. I'll take the electric field to be along the x direction. And this picture is really all I'm discussing. Don't worry about the equations or details too much. I apply an electric field. There is electron scattering, and that causes a net drift velocity in a certain direction, which drives a current. Okay, so I see a relaxation time. I have some scattering time tau. This gives me some net current. I can express the net velocity in terms of an electron mobility, and this will be important. I'll talk about the mobility quite a lot. Mostly we'll see that it tracks the scattering time and then some electron parameters. And then of course I can write the current in terms of the electron density, the net velocity, and this gives me an expression for the zero field Drude conductivity. It's just proportional to the scattering time, then some electron parameters, and the electron density. Turning on a magnetic field doesn't change this picture too much, except now I have this cross term from the Lorentz force, and so I'm going to have a velocity both in the transverse and the direction along the electric field. I can capture this effect with some tensorial mobilities. Now these are all in terms of the zero field mobility mu, and some additional magnetic field stuff. And if I just invert this equation correctly, find the linear response, I see that I can find the conductivity. It is now a tensor. There are some Hall responses, and additionally for the resistivity, there's longitudinal and Hall responses. What I want to point out is that the conductivity and resistivity both are the zero field value multiplied by some tensor quantity that depends only on the combination mu times b. B is never by itself. It always comes in multiplied by the mobility. This is really all that's going on in Kohler scaling, is that there's just the magnetic field effect only depends on the product, the mobility in the magnetic field, never just itself. So the magnetoresistance, which is just the relative change in the resistivity as I turn on a magnetic field, is only a function of this single parameter, mu times b. Typical Fermi surfaces should saturate in very strong fields. This is just because if we were to put this into a Boltzmann equation, there would be some information about the Fermi surface involved, but if I have a lot of cycles around the Fermi surface in a single scattering time, then that information washes out. And just to remind us what happened in aluminum, we see there's an initial quadratic rise. That's not so hard to stomach. You can see that the change in the conductivity is initially to decrease quadratically, and so you'd expect that. At strong fields, Fermi surface information is washed out, and we're left with saturating behavior. Now I want to also discuss how this can be used to understand some form of linear magnetoresistance that has nothing to do with criticality or anything about the strange metal nature. It's just about inhomogeneity and classical disorder. And this picture begins with modeling an inhomogeneous material. So here we have several resistances. It's kind of like a resistance network, as if it had some homogeneous dual. So if I apply an electric field to the sample, it responds with some linear response coefficient, and I'm just pretending like that conductivity were associated with some homogeneous system. Okay, now this is helpful if I relate the conductivity to an environment that is essentially averaged to be this homogeneous dual. So it's like a self-consistent mean field approximation. The net current through this system is essentially the spatial average of all the local conductivities times their local electric fields. And in the dual system, I have that it's just, well, in this case, there's an external field and homogeneous system multiplied by homogeneous conductivity gives me the net current. I make this self-consistent by saying the two must be equal. There's some classical electromagnetism here, but it's not so hard to work out. If locally each of these regions has a conductivity of the form we just discussed, so this follows Kohler's rule, it's just a zero field value multiplied by some mobility and magnetic field stuff, then we automatically get for free that this effective system, or this inhomogeneous average, will also follow Kohler's rule. So I can plot what we get from this effective medium theory calculation, when we get our curves that go from quadratic at low fields to linear at high fields. So these are not saturating. We can see, for example, just look at the blue one. We go quadratic at low fields and asymptotically linear at high fields. And these different curves are just different strengths of inhomogeneity, but not too important otherwise. And all it took to use this was that the inhomogeneity is large enough to classically average over conductivities. Okay, so how do we apply this to LSCO? There's some interesting data here taken. So this is scanning tunneling spectroscopy. So this is a spatially resolved image of a sample of LSCO near optimal doping. And we can see there's a local gap in homogeneity that's visually depicted here. And this maps onto a local density in homogeneity. And if we just read from this or check the paper, this length scale associated with this inhomogeneity is about 5 to 10 nanometers. Okay, that's nanoscale. It doesn't sound classically large or macroscopic in any sense, but we need something to compare this to. Let's look at the mean free path. If we apply just a standard layered material formula, what we need is that the mean free path is smaller than this length scale of inhomogeneity, so smaller than 5 to 10 nanometers. Thankfully, LSCO is a typical bad metal, so it actually has quite small mean free paths. Mean free path from this formula is about 5 nanometers at 50 Kelvin, so really pushing at the smaller regions in there. And it's the same size as the largest regions, the 10 nanometer sizes, at around 25 Kelvin. So anything above 50 Kelvin is certainly reasonably within the classical disorder regime, and down to 25 Kelvin it seems reasonable. Past then, you're outside of this regime. What's interesting is we analyzed in a recent paper some of the existing magnetoresistance data and found, in fact, that above 50 Kelvin, all of these curves could be scaled onto each other. So these are, the red ones here are all certainly within the classical disorder regime, and they seem to trace out a single curve. There is a mobility coefficient that I've multiplied on the horizontal scale, and that's temperature dependent, but that's standard. There should be a temperature dependent mobility that's tracing the scattering. Now what's interesting is this keeps going down to around 25 Kelvin. So here the dashed line is a linear extrapolation from the 50 Kelvin data. We're using the linear extrapolation of the resistivity above Tc to track down below the superconducting transition. So you can see the magnetic field initially suppresses superconductivity, and then we approach this curve. And it's really only at about 25 Kelvin and below that we start to see some deviations. At the lowest temperatures, below 20 Kelvin, we see significant deviations. These are clearly no longer the same curve. But that kind of makes sense from a classical disorder picture. This is right around when the mean free path is larger than the size of inhomogeneity, and it no longer makes sense to average conductivities. I know this was kind of a pedagogical talk, but I hope I can leave you some points here that we just derived. Above 25 Kelvin in LSCO, we have a bad metal with small mean free paths. nanoscale and homogeneity in the doping, and this quite naturally follows that we should see quadratic to linear magnetoresistance curves, and indeed we do, and they all seem to scale onto each other. Below about 25 Kelvin, this curve collapse breaks down. There is no way to scale these curves onto each other. Here we can see they're scaled onto the same slope and they just don't match. They're offset. The mean free path exceeds the scale of disorder, so a classical picture doesn't even make sense anymore. And the result that we kind of know already is this is no longer described by a classical disorder picture. And this is kind of an interesting puzzle. The T-linearity doesn't care about any 25 Kelvin scale, or apparently any scale. It's T-linear up to around 300 Kelvin, and it's not clear why the magnetoresistance should depend on anything down here, unless, of course, maybe it depends on this disorder scale. Okay, well, thank you for listening. I encourage you to check if you're interested into our recent publication. We talk about a lot more of the details here. And if you have questions, please email me. My address is here as well. Thank you.